from Group B2A, and today we'll share our analysis of LRT passenger ages, focusing on normality and gender differences. So first, we check if the passenger ages follow a normal distribution, the company assumed. We sorted the ages, calculated percentiles, and plotted them against Z-score. So the result near a straight line, meaning that the data is normally distributed with mean of 26.5 years and standard deviation of 5.6. Next, we tested if age differs by gender. So because variances were unequal, which is 34.1 for females and 21.1 for males, we used Welk tests. The result was clear. Female average 27.2 years and male 24.4, with statistically significant gap, which is with the p-value of 0.016. So what does this mean? Passenger age is normally distributed, but gender matters. So that's all from me. Thank you for listening.
Hello, my name is Puteri Afrina binti Muhammad Mustaqim. My matrix number is 240599190. I will briefly explain how we calculate the probability that the sample mean age is greater than 26 years. We start with the given value, which is the population mean is 26.9 years and the sample size is 100. Step 1, we calculate the sample mean, which is 26.46 years. This is based on the formula shown, where we add up all the sample value and divide by the sample size. Step 2, we compute the sample standard deviation, which came out to 5.654. This tells us how spread out the age are in the sample. We use this formula here. This means we subtract the difference between each value and the sample mean. Then, squaring those difference and adding them all up. Next, only we dividing that sum by n minus 1, which is 99 in this case, and then taking the square root. After calculating all that, we got S equal to 5.654. This is a measure of how much variation there is in our sample data. Step 3, we then calculate the standard error, which measure how much the sample mean is expected to vary from the population mean. The formula is standard deviation divided by the square root of sample size. That gives us SE equals to 0.5654. Moreover, step 4, we compute Z-score. This standardizes our result, so we can use Z-table. The formula is sample mean minus population mean divided by the standard error. That gives us a Z-score of negative 1.591. Step 5, we use Z-table to find the probability. We find the probability that the sample mean is greater than 26 years. So we find probability Z more than negative 1.591 from the table. That's approximately 0.9441 or 94.41%. So overall, there's a 94.41% probability that the sample mean is greater than 26 years. Now, let's interpret what the result means. The statistical results show that likelihood of obtaining a sample mean of greater than 26 years is very high, which is 94.41%, based on Z-score of negative 1.591 using a sample size of 100 and population mean of 26.9 years, indicates even though the population mean is slightly higher at 26.9 years. From a management perspective, this implies several key points such as sampling variability is expected. Minor deviation in the sample mean compared to the population mean are normal. The sample mean of 26.46 years falls well within the range of likely outcomes. Sample results are statistically consistent. The fact that a sample mean as low as 26 still has a 94.41% probability of occurring means that results are not outliers or red flags. They are statistically reasonable given the known distribution of passenger age. Next, passenger demographic remains stable, which means despite small difference between the sample mean and the population mean, the data suggests that the age profile of LRT passengers remains stable and consistent over time. Moreover, confidence in data quality, which is the close alignment between observed sample and the historical population data, supports the reliability of the sampling process and suggests no significant shift in ridership demographics. Additionally, no immediate action required that management does not need to respond to the small deviation in sample age data, as it falls within normal expected variation. In conclusion, the analysis confirmed that a sample mean age of 26 is highly probable given the population mean of 26.9 and the sample characteristics. The finding reassure management that current passenger demographic have not significantly changed and the survey data is consistent with existing trends. In this slide, I will be explaining how we calculate the probability that the sample mean age falls between 23 and 25 years. We are given a population mean at 26.9 years, a sample size of 100, and a sample standard deviation of 0.5654. To begin, we use the z-score formula, which is the sample mean minus population mean and then divided by the standard error. For the first value, we calculate z-score for sample mean of 23, so we subtract 26.9 from 23 and divide by 0.5654, giving us a z-score of 6.8977. Next, we do the same for the sample mean of 25. Again, using the same formula, we get 25 minus 26.9 divided by 0.5654, which result in a z-score of negative 3.3604. Now that we have both z-score, we check the z-table for their corresponding probabilities. A z-score of negative 6.89 is extremely far in the left tail of the distribution, so the probability is basically 0. For negative 3.36, the probability is 0.00039. To find the probability that the sample mean lies between 23 and 25, we subtract the probability at z equal to negative 6.89 from the probability at z equal to negative 3.36. That gives us 0.00039 minus 0, which equals to 0.00039. This means that the probability of the sample mean falling between 23 and 25 years is only 0.039%, which is extremely low. So, what does that very low probability tells us? A probability of just 0.039% means it is extremely unlikely to get a sample mean between 23 and 25 years. The z-score of negative 6.8977 and negative 3.3604 fall far into the left tail of the normal distribution curve. Probability of just 0.039% means it is extremely unlikely to get a sample mean between 23 and 25 years. The z-score of negative 6.8977 and negative 3.3604 fall far into the left tail of the normal distribution curve, indicating that such values are very rare based on our historical data. In the context of LRT passenger, it might point to a shift in the demographic. Perhaps younger individuals are using the service more than usual. This shift could result from recent marketing targeting younger groups, change in routes that are now more appealing to students or younger workers, or just a new patterns in how people use the system. Because this result is so unusual, it should not be ignored. It may be a sign that something important is changing. From a management point of view, this unusual outcome definitely warrants further investigation to understand the cause and whether any response is needed.
Hello there, my name is Adam Aidi bin Azri Aidi, and today I will explain to you how I do question 2A, which is I need to construct a 90% confidence interval to compare passenger satisfaction between two facility quantity items, which is seating capacity FQ1 and disable friendly features FQ2. For your information, if the passenger answer 4 or 5, we consider them satisfied. From our data, we can say that 51% of the passenger is satisfied with FQ1 and 66% are satisfied with FQ2. As you can see on my right, that is how I calculate the confidence interval, which is I use the confidence interval formula to find the difference between two proportions. From the calculation, I find an interval from negative 0.2633 to negative 0.0367. As we can see, the interval does not include 0. What it means? It means that there is a statistically significant difference in satisfaction. Lastly, I can say that more passengers are satisfied with FQ2 than FQ1. That's all from me. Thank you so much.
Hello everyone, my name is Yu Xiwen and my metric number is 240532216. Today I'm going to present question 2B. Test if the mean score on passenger satisfaction of the female passengers are higher than the male respondents at 5% level of significance. Given from the dataset 1, I calculated that the mean score of female passenger satisfaction is 3.5 and the mean score of male passenger satisfaction is 3.64 and the variance of female satisfaction passenger is 0.58 and the males is 0.45 and the sample number of male is 74 and the sample number of male is 26. And now we are going to move to step 1 hypothesis. I set up the null hypothesis is the mean score of female passenger satisfaction is less than the mean scores of the male passenger satisfaction. And the alternative hypothesis is the mean score of female passenger satisfaction is larger than the mean score of male passenger satisfaction. And let's move to step 2, test the statistics. And given from the formula, we calculated that the t-value is negative 0.88. Then next, the step 3 is to find critical t-value at 5% significance level. So we should calculate the degree of freedom first, and given from the formula, we calculated the degree of freedom is 49.31. And after we found the degree of freedom, we look up from the t-distribution table and we found the critical t-value is 1.6T7. Next, as the diagram shown below, we found that the calculated t-value is larger than the critical t-value and the calculated value is in the region of non-rejection. So we get the result. And in conclusion, there is no enough statistical evidence at the 5% significance level to calculate that female passengers has higher satisfaction mean score than male passengers. Thank you.
Hello, my name is Muhammad Sananda Rizky Azwan, and right now I'm gonna explain question 3. Okay, so question 3A, the hypothesis testing. In the first part of the analysis, we investigated whether there was a statistically significant difference between two groups, labeled FQ1 and FQ2. The mean difference between these groups was calculated to be minus 0.300, indicating that, on average, the value in FQ2 were slightly higher than those in FQ1. To determine whether this difference was meaningful or just due to random variation, we calculated the standard deviation of the difference, which was 0.870. This standard deviation helped us understand the spread of the data around the mean difference. Next, we compute the t-statistic, a measure that compares the observed difference to the variability in the data. Plugging in the numbers, we got a t-value of approximately minus 3.447. To interpret this, we compare it to the critical t-value of 1.985, which is the cutoff for significance at a 95% confidence level with 99 degrees of freedom. Since our calculated t-value is minus 3.447 had an absolute value greater than 1.984, we rejected the null hypothesis. This means the difference between FQ1 and FQ2 is statistically significant and not due to chance. Now for part B, the analysis of variance or ANOVA. The second part of the analysis expanded the comparison to multiple groups using ANOVA. First, we calculated the grand mean 3.936, which represent the overall average across all groups. Then we partitioned the total variability in the data into two components. One, between group variability SSB 0.330, meaning difference among the group means. And number two, within group variability SSW 66.910, difference within each group. To test whether the between group difference were significant, we calculated F statistic by dividing the mean square between groups. MSB equals 0.165 by the mean square within group MSW equal to 0.990. The resulting F value was 0.239. We then compared this to the critical F value of 3.9 at the same 95% confidence level. Since our F value is 0.239 was much smaller than 3.09, we failed to reject the null hypothesis. This suggests that while there might be a small difference among the group, they are not statistically significant overall. Thank you.
Hello everyone, my name is Nur Suryati Amani binti Anwar and my lecture ID is 24004891. So, as for the question 4A, we are required to do the chi-square test of independence. Basically, the chi-square test of independence is a statistical test used to check whether two variables are likely to be related or not. So, in this case, I already choose two variables, which is gender and private transportation. Both of them are under the categorical variables since this test is specifically designed for analyzing a categorical data. First thing first, I will state two hypotheses, which is the null hypothesis is there is no significant association between the gender and private transportation. Meanwhile, the alternative hypothesis is there is a significant association between the gender and private transportation. So now we move to the chi-square test statistic. Firstly, I will compute the overall population as you can see at my calculation down below. Then you will get the result of 0.54. Then I will generate a table of observed versus expected frequency in order for me to look at the data more easier and clearly. Finally, I can calculate the chi-square test statistic value. So I will use the formula in the green column, which is the sum of frequencies observed minus by frequency expected squared divided by frequencies expected. Then I will get the answer of 0.87 for 2 decimal places or 0.8708 in 4 decimal places. Now it's time for making a decision. Here, since the chi-square test statistic value, which is 0.87, is smaller than the critical value, which is 3.841, so we do not reject the null hypothesis and we conclude that there is no significant association between the gender and the use of private transportation among our respondents at the significance level of 0.05 and the degree of freedom 1. Now, we move to the question 4B, where we need to do the Mann-Whitney-U test, or also known as the Wilcoxon-Rank sum test. Mann-Whitney-U test is a non-parametric statistical test used to compare two independent groups when the dependent variable is either ordinal or continuous but not normally distributed. So here I already selected two variables, which is gender and age. It is suitable to use here since age is a numerical data under a continuous variable. First thing first, I will state two hypotheses. The null hypothesis is there is no significant difference in the age distribution between male and female group. Meanwhile, the alternative hypothesis is there is a significant difference in the age distribution between male and female group. Now, I will explain on how did I do the calculation for the Mann-Whitney test. First, I generate a rank tables in the Excels in order for me to calculate the sum of ranks for each samples. Then I will get the result of sum of rank 1, which is 249, and the sum of ranks 2, which is 76. After getting the result of sum of ranks, then I can calculate the U statistic. I use the formula as you can see at the table down below. Then I will get the result of U1, which is 4,450. Then the result for U2 is 2,199. After that, I will choose the smaller u in order to calculate the z statistic value. Then I will get the result of 3.97. Now, I will make a decision using a critical approach. So, for the significance level of 0.05, since the critical z value is negative 1.645, is smaller than the z statistic value, which is 3.97. Z statistic does not fall into the rejection region, so we fail to reject the null hypothesis. We conclude that there is no statistically significant difference in the age distribution between male and female groups in this dataset.
For question 4C, our group conducted a Kruskal-Wallis test to investigate whether there are significant difference passenger stratification based on education level. This is a non-parametric alternative to one-way ANOVA used because our data did not meet normality assumption. First, variable selection. We select the dependent variable as passenger stratification tree, which is safety and security. This measures how safe passengers feel using LRT service. The independent variable, which is education level, categorized into H, high school or below, B, bachelor degree, G, graduate or above. This variable is appropriate because it is a categorical with more than two groups, and we aim to test if stratification differs across this level. Moreover, test procedure is to perform the Kruskal-Wallis test. We rank all stratification scores across three groups, calculated the test statistic using H formulation, and we found the H value to be 3.82. The critical chi-square value at 0.05 with 2 degrees of freedom is 5.991. Since 3.82 is less than 5.991, we fail to reject the null hypothesis. Next, hypothesis. Null hypothesis. There is no significant difference in passenger stratification tree scores between education level. Alternative hypothesis. At least one group differs significantly in terms of safety and security perception. To conclude, the calculated Kruskal-Wallis H value is 3.82, which is lower than the critical chi-square value of 5.991 at a 5% significance level with 2 degrees of freedom. The p-value is 0.15, which is also greater than 0.05. Based on this, we fail to reject the null hypothesis. This suggests that there is no statistically significant difference in the safety and security stratification score PS3 among passengers with different education level, whether they are high school graduates, degree holders, or postgraduates. This finding is important because it indicates that passengers across all education backgrounds generally perceive safety on the LRT service in a similar way. Therefore, MFC management may consider that education level is not a key factor influencing stratification with safety and can focus on other variables such as service quality or punctuality, which might have a stronger effect.